Oh, okay. Hello, everyone. So, yeah, welcome back to the afternoon session. I would like to introduce Donn Hethcock. Donn and I go back a long time. We met in graduate school at North Carolina State, and he was helping me with theory of elasticity and almost kind of like a mentor for me. And actually, he got me, we're about the same age, but he got a job together working at Sharon Harris Nuclear Power Plant outside of Raleigh, North Carolina. And then later, we were both civil, mechanical engineers, structural mechanics, but the aerospace industry was hot, and we ended up becoming aerospace engineers. We both took jobs at LTV and Grand Prairie or Dallas, Texas, working on the B-2 stealth bomber. And then we kind of separated. He continued. I think he worked at General Dynamics on some kind of secret program. Over the years, he's been managers at different companies, Sierra Nevada, and of course, more recently here at EOS. And so he is, to me, a mentor. He's quite capable with structures of all sorts. And I'm glad that he's here today talking to us about actually our software HyperX on his application. Thank you.
Thank you, Craig. Yeah, I remember, I think we were both seniors at the same time, and I was a TA, so I was grading Craig's papers on the senior structures class.
How did you do?
He did really good. He had a big future ahead. But I think I remember he sent me a notebook in the early 90s, you know, containing all of his algorithms and his formulations for the original work he did that turned into hypersizers. So it's probably worth some money now. What do you think? So figure out how to turn these slides here. There we go. EOS Aircraft is developing a new sustainable regional transport aircraft. And we're currently operating in stealth mode, so I can't show you a whole lot, but I'll show you what I can. So what can be revealed? We are working on an electric hybrid clean sheet program, and working in a startup environment. And we've filled all the leadership roles. We've been hiring both U.S. and Canada. Been posting jobs recently up in the Montreal area. We've got an office established and hiring engineers up there. So it really represents the next leap in sustainable aviation technology. You know, it's a Part 25 aircraft, and we're going after the lowest cost of operation compared to any other regional aircraft, ushering in a new dawn of regional aviation. We're backed by some renowned investors and some airlines, and we launched the program last quarter of 2023, and our CEO is Michael Derman, and our Chief Operating Officer is Bill James, and then Luc von Bovel is our Chief Technology Officer, and he really was the one that originated this design. All we're showing is the nose of it, but I'm going to tease you with some other designs that he's been a part of in the past, and maybe you'll get a flavor of what he can do. And then on the engineering side, Thomas Greiner is our chief engineer. Kerry Manning is head of aircraft integration. And Joël Bordeaux is head of aircraft development. Chris Boschers is a co-author for this material. He's tech director and chief engineer at NIAR Atlas, the advanced technology lab for aircraft systems. Okay, so this is an early Luc von Bovel design, the Epic Victory aircraft that went from napkin sketch to first flight, I think. He claims in 183 days. But what does it really take to start something up like this? You know, it takes a vision. It takes a design that's attractive, because you have to attract investors, right? So a sexy design, a business case. You have to have a good idea of how you're going to make money and what the schedule is, the timeline, and what the aircraft performance is going to be. You know, is it going to be what the range and payload, and have those calculations done, obviously. And then, you know, what technology are you going to are you going to incorporate on the aircraft? I mean, is that technology ready? And how long will it take, and what will it cost to get it to the point where you can go in production to count on it? But really, you know, what comes first is really understanding the needs of the customers and the investors. And so looking at, to set up, you know, the aircraft trade studies, you have to ask, you know, what are the things you most need in a regional transport aircraft? And there are multiple, you know, customer segments that we have to inquire of, including obviously those who are going to fly on the aircraft, the passengers, the airlines that are going to operate the aircraft, and of course the investors and stakeholders in the aircraft. And when you survey them, you know, you find some overlapping needs. Some are similar, and sustainability was one of those. But you know, when you talk to the different customer segments, you get their voice in their own voice. So you have to translate that. Sometimes it's fuzzy and it's not really measurable. So we have to use a tool to kind of organize the voice of the customer. And this is just kind of an overview of what's called quality function deployment. I'm sure many of you have used this in the past, very familiar with it. But it's a subset of the requirements management you know, process. And so we take the survey data, the high-level needs, and we convert that, you know, what are measurable, what's critical to the satisfaction. So we derive that, and we build this first house up here. And then we look at what functions, you know, what it's going to take to move those critical to satisfaction metrics in a direction that customers want. And so those first two houses, including the roof of the house, which really captures the trade-offs, you know, which metrics, when you improve, are going to help other metrics, you know, and they're compatible, and which ones, you know, are contradictory. And so that really becomes some opportunity for innovation. But the first two houses are really solution-free, and that's how we set up the trade studies. So we go in, brainstorm some ideas, some solutions, and we look at the house, the roof of the house, and identify those contradictions. And we have some special ways to handle, you know, brainstorming through and resolving those contradictions. We evaluate them, and we pick, you know, the best features of a set of ideas, and then we tend to trim out those features that are more harmful, and we cycle the process and come out with a recommendation. And then we build the other two houses eventually, design parameters and process parameters. But the bottom line here is that when we show a customer what it is we're going to propose, it's going to satisfy their request. You know, they might not expect the solution they're going to see. So we want to delight the customers. Okay, so at the aircraft level, I mean, these are a set of critical to satisfaction metrics. And you can see that there's a couple of these that tie into sustainability, the life cycle energy use assessment, environmental regulatory compliance, how many dollars will it take to satisfy that? And so we establish the units and targets, and those also come from the MR&O document, the marketing requirements and objectives. And so we have to repeat this process, you know, at a lower level, you know, for the Aerostructures as well. So here's a list of different metrics at the structural level, and we can see that, you know, these also involve different customers. We'll have different suppliers that are involved. That'll have different capabilities, and we want to make sure that whatever solution we come up with, you know, gloves into what they can accomplish. Different parts of the airline organization, and then the engineering organization at EOS. So what resulted here was that the number one metric is weight efficiency, and it's really tied to sustainability as well as the energy to produce the material and manufacturing, raw material extraction, specific strength of material, and at the bottom there, the end-of-life disposal. How do you recycle the aircraft at the end of its life? So that begs the question, what is a pound of weight worth? So the first decision, really, what is the value of weight savings is what material do we use? And so to set up how we answer that question, we want to develop a cost-weight metric to serve as a means test for incorporation of weight reduction ideas. And so our approach would be to determine the life cycle energy costs for in-service operation and determine the energy costs required for representative flights over the expected lifetime of the vehicle, including some realistic assumptions on whatever segment ranges are, load ratios, margin requirements, and energy costs, and then calculating life cycle cost per pound, the threshold requirement, by dividing the total energy cost by the weight of the vehicle plus the average payload weight, and then the non-recurring cost per pound divided by the total non-recurring cost required to achieve the weight savings by the amount of weight saved. And then we amortize the life cycle cost savings to determine the cost per weight net present value. So we amortize recurring and non-recurring expenses required to achieve weight savings to a net present value and compare that to a threshold requirement. And the net present value of the life cycle cost savings determined by performing a business case evaluation over the assumed number of production units in fleet operations until the aircraft retires. So we can establish a hurdle for onboarding new technology by this calculation of the energy cost per pound. And some of the variables that we're dealing with are the mission range, the average diversion range, what percent we have to add on top of that, or distance, the fuel cost, electricity cost, the battery life, the battery density, the fuel used, the total fuel cost, the energy used, the total electric and energy cost, the payload fuel level, and effective payload, and the takeoff weight. So that just shows you some of the inputs that we use to calculate this value of a pound of weight. We also had to consider battery replacement and some interest rate. So we ended up with about $1,200 per pound saved. So if you consider, just making a material choice can be multiple hundreds, even thousands of pounds difference. And then looking at the number of aircraft, that are sold or that an airline would have in their fleet, that number can quickly, climb to a very large number. We're talking hundreds of millions, even approaching $1 billion. So once we amortize the cost, it drops down to about $850. So looking deeper at some considerations, some additional considerations to approach this material question, we note the weight fraction of battery modules and the related systems that support those modules can be in excess of 25%. Weight remains the biggest limiting factor for battery-powered aircraft. And even at 600 watt-hours per kilogram, the aviation batteries, are 20 times less energy dense by weight than jet fuel. So taking on that additional weight on the aircraft obviously is very challenging. And the right weight savings opportunity for the primary structure is needed to satisfy the business case hurdle. So any new approach to the primary structure must buy its way onto the program. And this technique allows us to make those decisions, that are data-driven. We want to, make and apply easy rules of thumb at this stage, in this conceptual stage, and find easy methods to look at relative weight comparison that are needed between, sets of metallic and composite configurations. We have limited access, to legacy weights databases, which really exacerbates our challenge. So as a starting point, we were working with a team of NIAR engineers. When you have a handful of engineers, you kind of use what their capabilities are, and some were already trained to use hypersizer. And so we built our GFEM, and we got the external loads on it and developed some shear and moment curves and looked at a cross-sectional approach using hypersizer. That was our starting point. And then we filled out this matrix, went back, and then as we refined our analysis and looked at other more details, we were able to actually consider a multidiscipline approach and morph our GFEM and then build on that. So hypersizer really provides initial results for airframe material trade, and it really enables, an electric hybrid aircraft. Okay, so these are some of the wing airframe configuration options that we put into our consideration. We had three metallic options: Z-stiffened, aluminum fastened, bonded Z, and advanced assembly, where we didn't have to drill on assembly. And then for composite, we're looking at a mixture of hats and tees and sandwich options. So with materials, aluminum, carbon epoxy, thermoplastics even, these geometry, stiffener shapes, and then for manufacturing processes, automation, AFP, infusion, co-cure or co-bond, and then for the thermoplastic, obviously welding. So, we utilize the stiffening options provided in hypersizer to evaluate the weight of the primary loaded structures. So here is our data kind of summarized and normalized, but it's this in-depth evaluation is really necessary to overcome, significant resistance over making a decision to go to composites. There's still a lot of experienced people in the industry, especially on the commercial side, for this size aircraft that are very resistant to make that leap from metal to composite. They've had some bad experiences, and they don't want to repeat those. And so we have to really dig pretty deep to convince them, to make that decision. So we're looking at, 11 design concepts. It says 10 there, but there's one more, I believe, against the 19 parameters that came out of the QFD. And we used hypersizer for the first pass, but then HyperX, we came in on the subsequent passes. The blue points are vendor quotes. The green, I think, comes directly from hypersizer. The brown are parametrically based, and a lot of those parametric numbers are weight-based, and then the red is just a WAG. And on the first pass, the initial wing airframe results show that the metal option is significantly heavier than the other composite options as a general rule. Some variation in cost, obviously, and on the weighted score, we end up making a recommendation for intermediate modulus epoxy AFP, co-bonded T-stiffened concept, and using that cross-sectional method with the hypersizer. So obviously, structural optimization tools were very useful to evaluate the trade study alternatives. Okay, and some additional details of the recommendation. We also looked at, obviously, the fuselage, the wing, and the empennage. The results showed an overall weight reduction of 27% on average, an all-electric range increase of 20%, and obviously improved corrosion and fatigue resistance. The cons were the recurring cost increase of 6.5% per aircraft. The additional capital equipment, to utilize composite would maybe limit the supplier base. There's less number of suppliers that have that experience. And then the non-recurring costs with the delta estimate at complete engineering costs as well going up. So fortunately, in our MRNO document, it stated that without compromising safety or reliability, The structure material selected should prioritize weight efficiency over other considerations, including cost and ease of manufacturing, for weight reductions of 10% or greater compared to other technologies. So this would seem to qualify, but we're still challenged with executive acceptance, and they tend to second guess, and they're continuing to challenge us to justify that recommendation. So again, just underscoring the rigor necessary to overcome the partiality toward a metallic solution. We gave the material recommendation, obviously using something that was already published to avoid a complete full qual, starting with that, knowing that the building block approach would cause us to have to test, specific details. But at least we start with some material specs, some published allowables, extensive use of automation to satisfy our rate. Smaller hand-laid up composites are not going to be very feasible economically. And then the use of metal, obviously for areas where those are still important, such as single load path components with lugs and clevises or those kind of details. Some components where you need some plasticity for such things as crash worthiness or bird impact, and then having sufficient conductive area to provide a return path, a ground path for the return network. And so we included, estimate adjustments for the lightning strike, for any min gauge thicknesses, for fuel tank areas or hail damage tolerance, and those type things. Okay, so this chart probably looks familiar. One thing we did take advantage of was having the Collier's engineering services, use of that. And so we did apply HyperX to evaluate some additional parameters, such as the stiffener height, the web angle, the crown width on the hats. And then we can see here that going with a 6-inch stringer spacing, we're still at very close to that curve that says none, which means no constraints. So that was good. And HyperX really was used to refine those parameters with the help of Collier and take producibility into account very early. So our counterparts over at University of British Columbia, reinforced that it's never too early to consider producibility. It's really no need to invest a lot of time looking into something you can't make, right? And then one of our engineers, Will Conway, I'll give him credit, pulling this slide together for me. We really recommend a starting point with a multidiscipline analysis and optimization tool. If you use HyperX, it does take time to build and modify a GFIM and make sure we have external loads done. But using a first order approach, we've been able to utilize NASA flops and some non-CFD drag tools approach, along with aircraft performance and mission simulation, to come up with a way to be able to cycle, thousands of iterations in days, to be able to find that sweet spot. I'm talking about changing the OML of the aircraft, other aircraft configurations. Obviously, if we save weight, but it increases drag, where is that trade-off as well? Okay, so in the background here, we see another one of Luke's early designs, the Diamond aircraft. But the role of optimization tools to address aircraft trade studies, it's really important that we wean off of parametrics to a sizing-based weights as early as possible. And this is especially important because there's so many unique systems that really aren't accounted for in the legacy aircraft that make up some of those parametrics. So we have to take those into account. Adopting other accelerated methods, such as model to margins, and I know that's really the emphasis that that Hypersizer and HyperX are working toward, but there's still, some areas taking local pressures into account, doing local global models. We still have some work ahead of us in that area. We did take advantage of some rapid mass property tools and some automation tools for external loads with the help of Bayer Flight Sciences. So we were very beneficial to have them on board. And we used HyperX in a number of trade studies, not just the material trade study, but also the wing parameters, wing attachment. How do we integrate the wing with the fuselage? Is it going to be integrated, independent, or some hybrid combination of both? And then location of high mass items. Locating battery modules on the fuselage presents unique challenges, and then moving those on the wing presents different challenges, but understanding the sensitivity, the weight sensitivity of that move, we utilized HyperX for that. And then main landing gear configurations, locations, stowed positions. It was very useful because HyperX is really practical enough to help us to use it for rapid iterations in our aircraft configurations. All right, so here we see another Luke von Bovel design. It's the Freedom aircraft from Sierra Nevada. So takeaways, establish and survey needs from each customer segment at the appropriate level, and use a systematic approach to affinitize or set their requirements up that are solution-free. Weight efficiency is the primary driver for a sustainable aerostructure. Use of MDAO tools first to explore the design space and establish the configuration in lines and take it into account those other parameters. And then structural optimization tools are very useful early in conceptual phases of the program for material selection, weight comparisons, and cost basis, the maturity of the configuration, and composite applications must be tailored for weight and manufacturing cost. So the use of HyperX drives those early material decisions and configuration trades. That's the end of my presentation.
Thank you. I was wondering how, when you implemented HyperX, how did that affect either just the amount of concept trades you could perform in a given time frame, or did it impact the time frame for a concept evaluation stage at all? Maybe if you could talk about how that worked relative to past experience or past projects.
I used Hypersizer on a previous, actually on this program, the Freedom aircraft. And it was very useful. It was useful because we had come up with a configuration that was proprietary, and we had to get some data to back up that approach. And I was very pleased that we were able to incorporate that data, and use it to compare to some other standardized approaches. And we got some unexpected results there that were very beneficial. So and that's why I quickly used it on this startup program, because I knew that it would leverage those results, a number of results and trades that we could do, leverage that up with the existing manpower that we had, for sure.
Thank you.
Related to the MDAO tools, what role did, I guess, your structures team or Hypersizer or HyperX have in feeding a multidisciplinary tool information about the different structural configurations?
Well, at first, for the wing parameters trade study, they wanted to know, what the weight of a certain configuration would be. And so we would have to go through and try and, size that, manually. So I wouldn't say that HyperX was an input to the MDAO tool. It was more of a go back and be able to explore the design space by using a first order approach, a simple, just a formula approach to be able to get a lot of cycles in and try and tune in on where that sweet spot is. Then once we have that, then use the update to the GFIM, update the external loads, and then use HyperX.
One quick question I had was in your material trade study, did you allow post buckling of the composite structure in the trade?
We had some pretty conservative stress engineers on the team, and without test data, they got a little scared. But we did allow some buckling prior to limit load, but it wasn't as aggressive as the metallic option.
How were you able, as a startup without a lot of test data, how were you able to predict the buckling loads for the composite, like the post buckling capability of the composites?
It was basically experience. People on the team had lots of experience, and Chris Bocher's especially, was able to share a lot of experiences that he's had on prior composite programs. Some of us, that worked on the military side, without aggressive, test data and use of composites, we couldn't satisfy, the requirements in the mission. So we had confidence it was going to work.
Your slides comparing metallic versus composites, the trade study that you did was interesting because I've always seen that larger aircraft composites trade better, smaller aircraft composites trade worse. So I guess my question, what kind of damage tolerance criteria did you use for the composite structure when in that trade study?
Yeah, for the damage tolerance, especially the fuselage for like the hail damage, a certain number of minimum plies for the crown, for hail. Obviously it was barely visible impact damage. But it's going to be, really, we have to get in more, we have to build up some test data and come up with a configuration and start into the building block. Because any configuration, that's going to save a lot of weight and it's aggressive is going to we have to build our confidence up with the test data to make sure that the damage tolerance is something we can satisfy. Thank you.
There's a snafu in Donn's awards.